Okay, thank you for the introduction. It's a pleasure to be here and give this talk. Basically, so we have two talks from Northwestern, and my talk is very much going to mirror what Peter Stanley just talked about. We're going to talk about, in my half, the methods we use for doing these reconstructions and how we do the calculations on those reconstructions. And then Scott's going to talk later about some of the studies we've done using this methodology. But as much as mine is similar to the first talk, we kind of go about a different method that he's alluded to, where we keep the structure as this voxelized structure. So using cubic voxels, and we actually only mesh it when we do surface area calculations, like you saw. But for the rest of everything we do, we keep it with this voxelized structure and do thresholding methods. And so the nature of this talk is more sort of the challenges we've faced along the way with doing it in this manner, and how we do our calculations, and just kind of bringing up issues that we've come across that hopefully can serve as discussions for possibly tomorrow or for today with other talks or question sessions. So a quick outline. Just going to start briefly with our sample preparation and looking at some of the images we've gotten with the FIB-SEM. Obviously, the quality of the images is paramount for automating this procedure. And that's really what all of this is aimed at doing, is being able to automate this segmentation procedure. As Peter alluded to, is kind of the rate-limiting step in the whole procedure. If you have to do anything by hand on a set of 400 images, the time adds up really quickly. Then we'll get into the image processing, some automated filters we run, the data analysis, different calculations we do, and then a few issues going forward that I think are worth discussing. So this is just our sample preparation. Maybe a couple years ago, we started filling our pore structure with commercial epoxy vacuum, filling the pore structure. Then we cross-section our sample and polish it, and mill this trench out. So this is kind of a zoomed out view with the electrolyte here. We can do either electrode, obviously. Just zoom in. We just mill out a square trench. The idea is to mill it out large enough that the redeposition on these sidewalls doesn't infringe on the area of interest that you're looking at. There are different geometries for this. I think we saw earlier you can do kind of a horseshoe mill. But as long as you can kind of avoid losing your view, either of these really works quite well. So this is kind of a history of our image quality and image development as we've been doing this over the past, I guess, 6 years now. And this was actually, I call it version 1.0, and this was way back in 04 and 05. This was a nickel-YZ anode, and this was just a bulk cropped image, so we haven't applied any filters. And all these images I'm showing are kind of what comes out of the microscope. And you can see, as Peter showed, there's some serious challenges with trying to identify what's here and segment everything. Then we realized at some point within that first year that you could actually get a very nice contrast mechanism between nickel and YZ in the Zeiss instrument, where you could mill and polish the surface at the same time that you collect an image. So instead of slicing, stopping the ion beam and collecting an image, we're actually doing a continuous mill through the material and then just taking a snapshot image simultaneously. And we're not exactly sure the mechanism for this, with some sort of surface charging. But you can see here, this is just an image of nickel YZ, and you can see some contrast here. This isn't optimized for it necessarily, but this is with the FIB off. And as soon as we turn the FIB on and start milling through, you start to see, obviously, these nickel particles that really are much brighter than the YZ phase, which is this gray phase here. So this is just an example of that type of image that we got. But again, you have all these issues with what you do with the open porosity. You can see that you get very nice imaging because you've got a high quality image of the interior of these pores, which shows up nice and bright. You get charging, and generally in our methods we're doing this thresholding method where if you threshold a higher color, you're going to get all all sorts of errors inside these pores. It's basically, you can't do it. There's just too many errors. So the option, of course, is to do it by hand. But as mentioned, depending on the user doing that, you can get bias unbeknownst to the user or known to the user. So the next sort of step we took was to, as I mentioned before, is to fill the porosity with commercial epoxy resin. And what this does basically is in the microscope, it shows up as a nice black, even phase. You can see the difference. These are basically the same sample, nickel YC sample. And also, when you get this nice black phase, you can really maximize the contrast between your nickel and YC because this stays nice and black for almost any imaging conditions. So this really helped in producing some high quality images that are much easier to automatically segment. With the epoxy infiltration, there are still issues. So this is just an example of cases where you get a lot of these little bubbles if you don't fill appropriately. A lot of this depends on your pore structure. You're trying to fill it with a viscous material, and sometimes it just doesn't fill completely. This is a case of high YC content, nickel YC sample. So this was 70 weight percent YC to 30 weight percent nickel. So in this case, you're actually getting a lot of isolated porosity too, and there's nothing you can do about that. You can't fill an isolated pore. So this again is a case where you run into these issues where this level set method has a lot of utility. And this is just a kind of final example of nickel YC image, kind of like the one I showed before. Just showing when you get a nice high quality image with very defined interfaces and very distinct three grayscale colors, that it's actually a fairly simple process to automatically segment through this. So in addition, we initially looked at just nickel YC anodes because we were having trouble getting grayscale contrast between the cathode materials. And I think it was around 2007, 2008, in collaboration with Dan Mum at UC Irvine, who had a ZEISS with this energy selective backscatter detector. So it's an in-lens detector that you can bias. So you're getting only, you also combine this with low energy, so 2 kV or lower SEM energy. You can bias the detector, so you're only getting the really finely backscattered electrons at high energy. It pulls out this backscatter contrast. You can see here, this is just kind of a standard SE image, and then with the ESP detector, the difference between the LSM and YC, which of course is what you need in order to reconstruct any of these. This is just an example of bulk image that we got for the cathodes. This is before any filtering. Pretty clear contrast between the materials. Again, it's not as good as these nickel YC images, but it's good enough that you can, with some imaging filters, you can do this automatically. So, summary of the image processing procedure. Generally, this might be a bulk image. Then we need to align all the images and crop them, and then run a number of filters to get this segmentation. And then all the calculations we do in IDL software. It's an interactive data language where we can program our own programs and calculate what we want. So I'm just going to go through a few of the kind of highlights of some of the filters we've developed to kind of deal with automatically segmenting. And this is actually the past year or two, a lot of work that Scott Cronin's been working on in MATLAB. This is very similar to what Peter showed with the illumination across the image. You can see it's much darker here than it is here. We kind of go about it a little differently. So we basically look at the histogram for each row, where you can do each column and plot that, and then fit a curve to it. And in the same manner, you can kind of throw out the high error points that are away from that, and then refit. And you can basically see that as you go, this is row number here. As you go down the image or up the image, the general brightness of the gray phase is changing.